Yeah, comes on everyone. So last thing we did was this. Great, let's go ahead. So next thing, this is a very important one. This thing comes at least in 6 chapters. So we can do this as a concept. Tension in a rotating ring. So listen to this. Top view. Let's say we have a ring of mass m and radius r. Is rotating with omega, right? And we need to find the tension in the ring. So this can be a question also. This will be a standard result. So we'll just put like a question only. So have a look at this, how to know this thing. The process is a little different. Mass is m, the radius is r, and this whole setup here is rotating with omega. So first of all, you need to understand why is there a tension in the ring. Think about it. If you look at the side view, it would look like this. The reason is this. At every point, if you take a small piece here, there is a centrifugal force. Remember, centrifugal force is away from the center in this case. If you stand on the rotating body, that means at every point, the centrifugal force is trying to pull these particles away from the center, because of which what will happen? There will be a tension in the ring, isn't it? Means if you rotate this ring, there is a chance the ring will start stretching. So the reason why you're getting the tension in the ring is because of centrifugal force. Centrifugal force stretches. Again, we are doing this in a non-inertial frame. Generating tension. Now we need to calculate that. So is that clear, everyone? Why is there a tension in the first place? So if you take something and rotate it pretty really fast, there is a chance it might break and it can explode also. It happened with me. Like I was in IIT second year. During that time, right, we didn't have all this hard disks and all. So the most common way of transferring data or storing anything was DVDs. So DVD ka, if you ever seen, right, they call it burning the DVD. When you put the data, they call it burning. So you put the DVD there and you have different speeds at which you can put the data. Right? If you take a slow speed, basically mechanically you're just rotating the disk there. Right? So if you take others, you need to keep your cams on or else you'll be removed from the classroom. So in that you have different speeds of data. So if you put it at slowest speed, the data will go a little slower. It will take a lot of time. So the fastest speed is around 8,000 RPM. Getting it? So generally it is not a problem. That itself, almost 4 GB of data takes around 8 to 9 minutes of transfer. So that was all fine. So, but DVD used to cost around 20 rupees that time. So one day, right, I was going out and someone was selling a DVD for 10 rupees. I was like, yeah, DVD is 10 rupees. I brought 2 DVDs. I took them. I was putting some, some data there. And then full speed, when suddenly there's a fart, karke, there's a big sound. I switched off the system, I opened the CPU, and I saw the inside of the DVD was shattered into pieces. Basically, it was rotating so fast. It's a cheap quality DVD, right? It couldn't withstand the kind of stress it generated and it shattered. Luckily, CPU was safe. I just cleaned up and it worked. But it can create issues. So this is one of the problems you face, when you are having this F1 racing cars. The wheels or the engine rotate so fast. If you don't use proper metals, the you'll get cracks in the engine and the axle wheels. So the kind of metal they use will not be the same thing which you use in a regular vehicle. They have to use some special, kind of alloys. So let's see how this goes. So we have the ring here. We are considering a small piece here. I'm exaggerating the figure, but RD theta is very small. So my observer is standing on this. Now, if you try to draw the FBD of this small piece, like I said, I'm exaggerating this figure here. The tensions will be along the string tension. The centrifugal force will be dm omega square r. The whole angle is d theta, so this will be half angle d theta by 2. This angle is 90 degrees. This will be 90 minus d theta by 2. This will be d theta by 2. Similarly, this will be d theta by 2. So if you resolve these forces into components, we will get t cos d theta by 2. This will be t sine d theta by 2. Now remember, even if you have a massless string, still you'll get tension. This is t cos d theta by 2, and this will be t sine d theta by 2. And you can clearly see here the two vertical components, 2t sine d theta by 2, are balancing the centrifugal force dm omega square r. What is dm? dm is mass by total length, which is 2 pi r, into that small length, which is r d theta, which is md theta by 2 pi. That is one. And second thing, for small angles, sine theta is equal to theta, approximately theta. So be careful here. If I say sine 2 degrees, what is sine 2 degrees? When I say small angles, right, generally we say theta less than 5 degrees. So if I say sine 2 degrees, how much is this? 2. Convert degrees into radians first of all. So sine 2 degrees is sine 2, 1 degree is pi by 180 radians. So this is approximately equal to pi by 90. Don't say sine 3 is 3. It should be in radians. So for small angle, sine theta becomes theta, and d theta is very small. So this is 2t d theta by 2, and this is m by 2 pi d theta. You should have seen this once. 2 2 will cancel, d theta will cancel. Tension is equal to m omega square r by 2 pi. Pretty standard result. This again you will encounter in surface tension, elasticity, waves, electrostatics, magnetic force. Getting it, this will keep coming. At least 6 7 chapters, you will see the same logic every time. So especially remember the way I did that. More than the result, the process is more important. What was the process? I took a very small piece, meaning I'm exaggerating the figure. In reality, RD theta would look like this. You're getting it? That is the RD theta we're talking about. It's very small, almost negligible. So the two tensions ka vertical components are balancing the centrifugal force, and the horizontal components cancel out. Do check out the process. So if you take a ring and start rotating with omega, because of its own centrifugal forces, the ring will start getting a tension. And if you can really rotate it pretty fast, there is a chance the ring will shatter. like this.
Hello, I'm Gav. I'm Dan, and this is the slowest Slow Guys video we've ever done. Pretty interested into a lot of
So these people took a CD and they're rotating it at pretty high speeds and they're recording it with a high-speed camera. We'll just go to that part. So there we have a disc rotating.
Oh man, not yet.
I hope you can see that small disc there. And gone. But did you see? It just blew up like a balloon. It just blew off like a balloon. Now, if you see that in a slow motion, there, did you see? This is, I think, there's 100 times slower, but still you can't see it clearly. Look at that CD there.
2,500 frames a second isn't nearly fast enough to see what happened there.
Now, if you just slow it down more,
Let's look at what we got. Right. You can see it walking. Look at that. Whoa. Look at the shape of it. It's moving. Like the whole thing. Whoa!
yeah, did you see how it exploded?
That looks amazing. Literally just shattered.
If you see that in more slow motion, see.
No, I'm gone. I'm out. I'm done. Oh, that's amazing. See that again.
1100 times slower, but still it's not clear, so they do record it again.
All right, Daniel. Full speed. Full speed ahead.
And then they kept even a shape also.
Okay.
It's 28,000 RPM they're rotating it at.
This is satisfying to turn. Is it? Yeah.
You can see that how it just explodes. This is the same thing that happened with my
You can
CPU.
actually see it warping in real life. That was awesome. I jumped. You jumped? Yeah. That'll happen eventually. That's the thing when you're framed, you get to a moment where something happens, it takes forever to get to. That was...
And there, see, now it happens.
Oh,
Can you see how it cracked?
that was awesome.
So basically, even though we say CD is made of uniform material, it will be it's not uniform everywhere. So it starts breaking at one point and then from there it spreads. You can see how it spreads.
And the cracks in it were perfectly like the direction the
See how the cracks spread?
So it was like a spiral effect.
There, you can see how it is spreading the cracks. And this is what I told you, right? If your centripetal force or the tension goes off, they will fly away tangential. And look at how the particles fly off. They just fly off tangential.
Turbine, that was cool. All right, so that was at 62,000. Yeah, to 384 by 257.
I think there you can see it more slowly here.
Oh, look at that. That's awesome. Just the shape it makes when it shatters. Like a little tree.
Yeah, that's how the crack starts and goes up.
That is amazing. It's wicked. That is amazing. It goes like either side of the middle.
So that's what can happen if you really rotate fast. And this is the tension there, omega squared by 2 pi. We did it for a ring, it's valid even for a disk also, it will be something similar. Clear with this? It's a pretty good question, standard result. This, when it says something similar again will come in other chapters. You'll encounter this at least 6 times more. So do keep this in mind. Let's go ahead, next one. Any doubts on the process, please ask me. You can't find, that has to be given, metal has to be given. It depends on the material. What if you put a steel disc? It'll take more omega. Next one. Next one. Something similar, but this time we have a rod here. The rod is rotating with omega. This is x is equal to 0. This is x is equal to L. Mass m. So this rod is going in a circle like this. So rod of mass m is rotated in a circle. with omega. You can neglect any gravity here. So at a distance x, so from the center, if you take a distance x, find the tension at a distance x. At a distance x from the axis. It's a good one. Give it a try. How do we find the tension in the rod at a distance x? Let's see. That's not the answer, Arush. There is a small trap that I think that thing you messed up. Let's see. Now listen carefully again. These kind of questions, right? You should have an idea once, but the thing is, these kind of things keep on coming. Then you should know, okay, this is how I should take an element. For example, look at the previous question. If you see this question for the first time in the exam, it doesn't click. But the point is that only. The reason we do in a class is I am trying to show you as many different possibilities as possible, so that when you go to an exam, right, you'll be able to see and say, like, okay, this thing looks like this, so I just need to change here, and then it works. So that is the whole point. So don't think like, you'll go to the exam and you'll do everything from scratch. Tomorrow, if you become an architect, the first thing they'll make you do is they'll take the top 100 buildings and they'll make you draw and they'll make you design each and everything again and again and again. Not because they want you to buy the 100 models. When there's a new project that you're doing, they want you to take ideas and inspiration from different models and how they handled different problems in different models and use them. We are doing something similar in the class. So if I'm teaching you 10 problems, there is a high chance you won't get all 10 of them. That is completely fine. That's a good thing. That means you got to learn new stuff. If I teach you 10 and you got all 10 of them, that means I'm bluffing you. I'm not teaching you for advance. Right? So don't compete with me in the, class ka thing. You're here to learn. You want to compete, do that in the exam which I conduct every week. In that exam, you need to score, not in the class. So let's see how to do this thing. So some people, right, last time they were saying, sir, whatever questions you give in the class, we don't get. I said, that is good, right? That means I'm teaching you something new. So don't worry about that thing. That is completely normal. So how do we handle this? So listen carefully how to choose an element here. The problem here is as you go, every point the tension is changing. So this is what we do. We done something like this, but this is a little different. So at a distance x, we will take such a small piece dx. Can someone tell me here at which point on the rod the tension is maximum? At x is equal to 0 or x is equal to L?
X is equal to L.
Wait 1 sec. I think my mic is on. Bolo. Where? Where do you guys think the tension is maximum? X is equal to 0 or x is equal to L? Okay, let me ask you in another way. Now, if you look at each piece here, each piece ka centrifugal force is outward. Now, you tell me if there's a number 1 person here, someone is pulling with F. Number 2 here, they're pulling with F. Number 3 is pulling with F. Number 4 is pulling with F. And number 100. Now, you tell me which person is feeling the maximum tension in the hand? 1, right? Same kaha pe record. This number 1 guy has to balance this 99 people ka force. Everyone is adding extra force F and F and F. Look at this thing. If I take only this point here, I have to only oppose this many centrifugal forces now. If I take here, I have to oppose all these centrifugal forces. So if I take at the axis here, I have to oppose all the centrifugal forces. So where is the tension maximum? At the axis, isn't it? At x is equal to 0, the tension is maximum. And the tension is 0 where? Tension is 0 at x is equal to L. There is no one to pull you only. So that is the first thing you need to understand. Tension is not 0 at x is equal to 0. So let me just put that here. So when you take this rod here, it's like, think of like this. You're just standing here. If one person is pulling you and second person is pulling the person 2, person 1, and 3 is pulling this thing, you have to balance person 1, 2, 3. So your tension will be 3T. Whereas the person 1 has to balance only 2 and 3. I hope you're getting that. So for each piece, if you see, the centrifugal forces will add up like this. That means the person standing here, x is equal to 0, balances all centrifugal forces. From x is equal to 0 to x is equal to L. Therefore, tension is maximum. Whereas if you take some person here, let's say x is equal to 2L by 3, then this person balances all centrifugal forces from 2L by 3 to x is equal to L. And if you look at this guy, x is equal to L, there are no forces only. There is no one on the right hand side to pull him. Therefore, tension is 0. So it's a pretty good statement there. You can use this. So free ends have 0 tension. What is the meaning of free end? This thing. It is not attached to anyone. It is not tied to anyone. Such a thing is called a free end. Hansh, clear, na? That is, x is equal to L, the tension is 0. This is the first thing, everyone. Tension is, as you go to the right side, tension is decreasing. Now, when you look at this piece here, take a small piece here, draw the FBD. What are the forces? T plus dt. T, the centrifugal force, dm omega square x. So every small piece, the tension is increasing by dt. Now, again, here one more thing. Mathematically, whenever you integrate, right, Max really doesn't know whether the function is increasing or decreasing. So what we do always, mathematically, we always assume the function is increasing, but we know actually it is decreasing. So see, let's see what happens. Mathematically, we always assume functions are increasing. So, and dt is the tension for that small dx. So dt is the additional tension that extra tension force because of the centrifugal force. I hope everyone knows what is dt by now. We have done this before also, T and T plus dt. So we are saying dt is an additional tension in dx. Have a look at this page. Let me write the equation in the next one. Anything that you didn't understand here? There are a little bit of new things here. Clear? Then let me just show that FPD again. So in that small piece, the forces are T plus dt. This was T, and this is the centrifugal force. Now I said, as you go to the right side, tension is increasing. But mathematically, I took it as tension is decreasing, but I said mathematically it is increasing. See what happens. So T plus dt plus dm omega square x is equal to T. T will cancel there. I got minus sign. So you assumed mathematically tension is increasing, but the science will take care of it. Make sense? So dt is not positive. So the more you go to the right side, it is decreasing. Minus sign indicates that. And then what is dm? Dm is nothing but total mass by total length into the dx piece. So we have dt is equal to m by L omega square x dx. Now this is where most people mess it up, which some of you did actually. What are the limits? When you say tension 0 to T, is tension 0 at x is equal to 0? Where is the tension 0? Tension 0 at x is equal to L. So be careful. Always don't put 0 to T and 0 to x. The meaning of limits is when you say T is 0, where is T is 0? T is 0 and x is L. This T is the tension at x. This is the mistake some of you did. You took 0 to T and 0 to x. The limits are L to x. Tension is 0 at that. So we get T is equal to minus m omega square by L. X dx is x square by 2. Limits will go from L to x. We get minus m omega square 2L. X square minus L square. We get m omega square L square minus x square by 2L. This is your tension, everyone. Then you can clearly see at x is equal to 0, we have maximum tension, which is m omega square L by 2. That is the maximum tension in the rod at axis. So at a distance x, this is a tension. Whoever got m omega square by 2, that you just goofed up the limits. That is the only mistake you did. Please have a look at the steps. Clear, everyone? Any doubts on this? Can I go ahead? Vignajit, Ojas, Vihan, Puruja, Krish. Go ahead, Arush. Next one. So we have a rod like this, and we have a spring here. So let me show this. So we have a rod here. There is a L-shaped rod here. You attached a mass M here like this with a spring. I hope you're getting the diagram how it is. This is O, this is B, and this is A. So that mass is A. This is length L. This is length L. And this angle is 90 degrees. So angle OBA is 90 degrees. So this whole setup is rotating. So the spring constant is K. Getting it? You can neglect all the gravities here. There's no gravity. This thing is there, this jacket kind of thing. This is like a hook. That is mass M. It's like a bead. So one end of a spring is fixed at point B. It is fixed, okay? It is attached to point B. And the other end is attached to a mobile mass. So this M can move front and back. It's like a, you can see how it is. It's like a rod which can, just move around it. And the other end is attached to a movable mass which is free to move. Now, if this whole system rotates with omega, find the elongation in the spring in equilibrium. Find max elongation in the spring when it rotates with omega. So you are rotating this whole setup with omega now. I hope the diagram is clear, everyone. Let's get this. Let's see. It's actually pretty straightforward. The thing is, see, when you're, again, step one, choose a system, draw the free body diagram. Now, when you draw the free body diagram, this is going like this. This is R. This is your centrifugal force, m omega square R, away from the center. Isn't it? Centrifugal force. The observer is standing on the body, okay? The spring force is this way, kx. This is 90 degrees. Let this angle be theta. So now if you try to resolve the components, you will realize if that is theta, this is theta, this would be m omega square R cos theta. Agreed? So the entire centrifugal force is not stretching you. Only a component of it is stretching you. So m omega square small r cos theta is equal to kx. Meaning the diagram would have looked like this. This is in 90. This is theta. This is theta. This is your centrifugal force m omega square r. This is the spring force kx. This is the component of the centrifugal force m omega square r cos theta. We know this is r. This is perpendicular to what?
Perpendicular to the whole rod,
What is perpendicular?
the centrifugal force.
Is it perpendicular? Centrifugal force should be which way?
Outward.
So if you see from the top view, if it is like this, and if this is the center, so according to your logic, centrifugal force will be this way. But where is the center? So it will turn like this and go centrifugal force toward the center.
Oh. Okay, sir.
No, it has to be away from the center because observer is on the body there. Then yeah, you're done. So that is R. And so what will be this length then? This is already the elongation, remember? The spring got elongated, so it is L plus X. X is the elongation. And you're done. So R cos theta is equal to L plus X. Is that making sense for the triangle? If you look at the right angle triangle, this is O, this is A, and this is B. AB has become L plus X because the thing has stretched. This would be L plus X. Substitute there. So it is m omega square R cos theta is L plus X is equal to Kx. Bring all x to one side. So this would be m omega square L by K minus m omega square. That's what we had to do. Check it out. Clear with this? Navihan? So the main idea is that centrifugal force will not be perpendicular. It will be away from the center. A component of it is actually stretching the spring. The other component is actually generating normal reaction, which we are not interested here anyway. The rod is smooth. Next one. Any doubts on this? Clear, na? Ahana, Ishana, clear? Arnav, Taksha? Taksha, clear with this. Next one. There, we got a disc here with a groove. This is a disc with a smooth groove. Meaning top view, if you look at it, basically you made a small groove in this thing, a hole kind of thing, and inside that you kept a block of mass m. Initially the distance is r/2, and then you started rotating this whole setup with omega. Now once you rotate, what will happen? It won't stay there, right? It will just come out. So if you actually try to see the path, it will actually something like this. It will start spiraling out. So the block spirals out. This will be the path of the block. See, it is going in a circle also, it is coming out also, isn't it? It is spiraling out, isn't it? Find the speed of the block when it comes out of the groove. Initially it is r/2. Omega is constant. You are rotating the disk with a constant omega. Find the speed of the block when it comes out of the groove. I hope the diagram is clear. Anyone didn't understand the diagram, please ask. Just give it a try. Just get some water and come. Root 3 r/2 omega. That is wrong. Right, Vihan. How do we do this? See. Now it is very difficult to solve this in the ground frame. We don't understand what is happening. But if you solve this problem in the non-inertial frame, that is a blocker frame, that means my observer is always standing on the block. And if you ask him to draw the FBD, he will say the reason you're getting out is because of centrifugal force. So he will say centrifugal force is m omega square x, and the block is coming out with acceleration a. Actually, the observer is just below the block. He's not on the block. He's always standing on the wedge below on that rotating disk. So that's it. M omega square x is equal to ma. So we get a is equal to omega square x. A is v dv by dx, which is omega square x. So we get V dV is omega square x dx. Then integrate. Limits will go from 0 to V, and this will go from R by 2 to R. This will be V square by 2 is equal to omega square x square by 2. Limits are from R by 2 to R by 2. 2 will cancel. We end up with V square is omega square R square minus R square by 4. We end up with V is equal to root 3 by 2 R omega. But be careful. What did we get here exactly? This. Now, tell me one thing. If you're standing here and looking at this, what will you think? You think this is going out, right? What you got here is, this is the radial velocity. Because what is this acceleration? This is radial acceleration. This is an acceleration away from the center. That means when you integrate this, what you get is also velocity away from the center. This is your radial velocity. That means when you come out, actually something else is also happening. Think about it. So when you're coming out, when the block is just about to fly out, one, you have a radial velocity, but you're also going in a circle, right? So there'll be also V tangential, no? Isn't it? You are also going at a circle. So at that point, you'll have a V tangential. So the particle actually flies at an angle. Try this and see. If you put some duster or something, or put some coin on the fan and switch it on and see. The coin will fly at an angle. It won't come out radially outside. So the speed will be root over V tangential square plus V radial square. There are two components. V tangential is how much? R omega. V radial is how much? 3 by 4 R omega square. That would be root 7 by 2 R omega. Check it out. So the main idea is this. I'm sure most of you did get the radial velocity after integrating, but what you forgot is this is the velocity away from the center. You will also have a velocity which is tangential. That is the reason. Look at the path. Did you see? I didn't draw like, coming out like this. I showed it at an angle in the path also. See how it is spiraling out. Meaning logically also you can see every instant, look at this velocity. There is one part away from the center, one is tangential. It is not going in a circle. There are two velocities at every instant, radial and tangential. Most people forget the tangential part. Have a look at this. Any doubts on this? Any step you're not convinced, please ask. Clear? Next one. Now let's see some theoretical based questions. Ever been on a giant wheel? Right. So let's say we have a giant wheel here. Giant wheel rotating with omega. Now in this, when it is exactly horizontal, there is a seat here. And you're sitting inside. Now the question is, if I take the forces here, A, B, C, and D, like this. So there are four options I gave you. In which direction does the seat exert force on the person? Examine, they'll give like this one. Options are A, B, C. There are four directions I gave. Approximately which direction? We don't need to know the exact values. in which direction does the seat exert force on the person? Yeah, most right, Arush, who was just behind. Try others think. I'll give another 20-30 seconds. Let's see. See, if I draw the FBD of the man, the person there, what are the forces? The seat is pushing you up, so there is an Ny, your own weight Mg, and the seat is also having an Nx. There's a horizontal, the cushion, and the centrifugal force is dragging you outside. Making sense? So Nx and Ny belong to the seat. So when you look at this thing, so the seat is pushing you with Ny, and this is the Nx. This is the force due to the seat. Just think about it. Right now, you're sitting in a chair. What is the chair doing to you? The backrest is pushing you forward. The bottom part is pushing you upward. So there are two forces, right? The answer is B. So here Nx and Ny are components of the seat. Easy one. But they do ask theoretical questions. Let's see one more like this. Suppose an aeroplane is going in a horizontal circle with speed u. Okay. R is the radius, M is the mass, and let's say F is the thrust force due to the engine. So engines are generating some force. Which of the following is the free body diagram? Like this, they'll give 4 options. Out of these 4, which is the free body diagram of the aeroplane? That aeroplane is going on the blue circle. What do you guys think? Hey, Puroja. Be careful here. In the question, if nothing is mentioned, he's always asking in the ground frame. Whenever they say draw the FBD and they don't say anything, he's talking in the ground frame. Now you tell me, if the observer in the ground frame, will he see centrifugal force? The centrifugal force is something you created for your convenience to solve problems. It doesn't exist. If nothing is mentioned, assume observer is in ground frame. So what is the answer? C is the answer. Why C is the answer? Think about it. So when the plane is going in a circle, you need one component, F cos theta, to balance mg. And you need one component, F sin theta, to provide centripetal acceleration. Na? You're getting it? Since you're going in a circle, there must be an acceleration someone has to provide. So engine ka one component is making you go in a circle, and engine ka one component is balancing your weight. And this question is same as this question, isn't it? Conical pendulum. What is the difference? Tell me. Here, the tension is doing the same job as the engines are doing in the plane, isn't it? Is that making sense? So whatever the string does here, the engines have to do the same thing. So the engines are putting a force at an angle like this. This question is same as the aeroplane, a conical pendulum. This is similar to conical pendulum. Answer is C. So the idea is the idea. If I don't mention anything and I say draw FBD, I'm asking in the ground frame. So the first two options are gone. Centrifugal force, there's nothing there. And D can't be the answer because if you're going in a circle, there must be a force toward the center. There is no force toward the center. That F is away from the center. This is similar to a conical pendulum. Clear? Any doubts on this? Next thing. Turning the page. Clear, na, Sharman? Going ahead. Krish, clear so far? Jainil? Devansh? Niharika? Perfect. Next thing, banking of roads. What is this banking of roads? I'm sure you must have seen this, whenever you're going on if you're going on Pune Expressway, right? And whenever you must have seen the roads take a turn, you'll observe the roads are not flat. They're actually little elevated. So the thing is, whenever you're building roads, the curved sections of the road are at an angle are constructed at an angle theta with the horizontal. You'll see why. This angle is called banking angle. Meaning this is what they do. If you look at this, this NASCAR car, racing car, tracks, they're quite steep actually. They almost put 31 degrees. In normal highways, you generally have around maybe 8 to 12 degrees, depending on how fast you want to go or how steep it is. But these racing car tracks, they have almost angles of 30 degrees. Now let's see, why do we need to do this? First, let's assume you're a civil engineer, right? And you got a contract to build a road and you designed a road which is flat. Case one, rough, horizontal, curved road. Means you didn't put any banking. So if you look at the top view, your road will be simply flat. And now see the problem here. So a vehicle enters this track and it goes in a circle with some speed v. Since it is going in a circle, it should have a centripetal acceleration. So friction will come this way. So this friction must provide the centripetal acceleration m into AC, which is nothing but mv square by r, which is less than equal to mu mg. That means we have v is less than equal to root mu gr. Now there is a problem. We got a speed limit. What this thing is saying is, as long as v is less than equal to mu gr, this is a condition for no slipping. You won't slip. So if you're going on a road without banking, you can't go faster than this. If v exceeds root mu gr, the car starts skidding. What is the issue with that? The issue is, think about it. Let's say there's a curved road. Morning, you're going in a car. Let's say you're going at 60 and the car was fine. Evening, while coming, it started raining and the road became little water and all became smooth. So mu value will decrease. So that same car, morning 60 didn't happen anything. Evening, it slips. Let's say you brought a new car from the showroom. The tire is good and all. So you go at 70, it is fine. After using the car for 1 year, the car tires will become a little smooth. The car slips. You getting the problem here? Suddenly you don't have control over the speed. So new cars will go fine, old cars will slip. If it rains, you will slip. If it doesn't rain, it is fine. Meaning you designed a very bad road where you don't have any control over the speed. Or the same road, if you keep using, after maybe 2 years or 3 years, the road itself will become smooth. Vehicles start slipping. So you made a road where you don't have any control over the speed limit. So the biggest problem is this. So this mu depends on condition of the road, environment, a lot of things. It depends on condition of road, vehicle, and climate, environment, everything. So we don't have any control over the speed. So this is a pretty bad road. You don't want to design a road like that where you don't have a control. Clear? The second case. Now let's say, how does this banking help you? All clear with this page? So this is a decent result. So if something is going on a curve which is flat without banking, you can't go faster than this. You'll start skidding. You must have seen this, when you're going in a cycle and it rains, ever skidded? Ever took a skid when you're taking a turn? Ever happened? This is the reason. The mu decreased and your maximum speed has decreased and you can't go more than that. Let's take case 2. Case 2, let's take smooth, but the road is banked. So the curved part of the road you built like this at an angle theta. So your vehicle is here. This guy is going in a circle like this. So that is a circle it will go in. Now, if you try to draw the forces, you will find normal reaction. You will find your own weight mg, and there is a centripetal acceleration. So I will just draw the FBD again in a 2D view. In this view, look at the forces here. This is normal reaction. This is theta. This is 90 minus theta. So if you look at the components here, this is n cos 90 minus theta, n sin theta. This is n cos theta. This is your mg. This is your centripetal acceleration v square by r. So n cos theta is balancing your weight, and n sin theta is providing the centripetal acceleration. So here, who is the centripetal force? N sin theta. This is the centripetal force. Which is mv square by r. If you divide them, you end up with tan theta is equal to v square by rg. So we get v is equal to root over rg tan theta. And did you observe one thing? Independent of mu and independent of the mass of the vehicle. Means if you make a road like this, and again remember, the thing is, in the previous question, the friction was the primary thing, isn't it? Friction was the main reason you're going in a circle. But in this case, there's no friction only. The one who is making you go is your n sin theta. Friction here is a bonus, isn't it? That means if you say speed limit is 50, because there is a friction, you can go even at 55 and you'll still be safe. So friction becomes a secondary factor here, which will, help you. Even if you exceed the speed limit, you're still safe. It becomes actually a safety factor. And the biggest thing is you made a road which is independent of the weather, independent of mass of the vehicle. It doesn't depend on anything. R is in your hand, G is anyway constant, theta you can construct. So before making a road, you see how much space you have, what speed limit you want, and accordingly you can make the angle. So this thing here, tan theta, v square by rg, this theta is called banking angle. And v is called banking speed. So sometimes they'll say like this, the road is banked for speed 30 kilometers per hour. Why n is mg cos theta, Vihan? So,
Sir, means in the other problems of NLM, we used to take it like that.
Okay, so this is the other problem. Ask yourself, no, is this the other problem? There's no difference only between this and the other problems.
No,
There's
sir,
no
there's
difference.
difference.
They're exactly the same. Not a single difference you can notice anywhere. You couldn't notice anything?
Sir, circle.
So, अरे God, if you take n is mg cos theta, then you had centripetal का component भी लेना पड़ेगा. In other problems, you never had centripetal acceleration. The block was simply sliding up and down.
Okay.
Got it? If you want to take in this direction, then you have to take acceleration का component also, na?
Yes, sir.
If that is the case, why didn't you do this thing in that way then? A problem है, why didn't you say T is equal to mg cos theta? If you do that, then acceleration का component भी लेना पड़ेगा इस direction में. Don't blindly write the forces. Always when you draw an FPD, understand. Remember the third step? Resolve the forces and the accelerations along x and y axis. So there is an acceleration component here. You can't do that. Is this clear, everyone? So
Yes.
if you bank the road, you are making a better road because you have more control. So you can put a speed limit on the road and say, the speed limit is 40. So it is understood, like, if you can, even without friction, you can go with 40. And if you have friction, it is an extra bonus for me. So we will see the next part, that what happens if you have friction also on a banked road. But do have a look at this page. Anything that you didn't get, please ask.
Banking of roads 01. Objective. To earn earnings and speed
Now
while
see.
taking a turn. When a car takes a turn, each curvilinear section of the turn can be approximated to be an arc
So
of a
this, what he's
circle
showing is a road which is horizontal,
with a certain
but
radius.
curved road, but not
The
banked. It's flat.
centripetal force must act towards the center.
This is all that equation which I wrote. So there is a friction here on the tire. You can see how it is. Since there are 4 tires, 4 frictions,
Normal force
4
N
normal reactions, but
balances the
all
weight
4 N
of
will be equal to
car
mg.
If the center of the
I was going to write the equation.
is force will be such or equal to
And there we got that. So V is less than equal to root mu r.
If the car
moves with a velocity greater than the
If you go faster than this,
it skids away from
that
the
is what
center.
happens. Now this is what I was saying. See, now the same road, if it starts raining,
Banking of roads.
see what happens. The friction has become less. Your
Always
maximum
allow
speed has
friction,
decreased.
as it depends on external factors such as rain or frost, which significantly decreases the value of static friction.
You getting the skidding?
To avoid skidding of vehicles at turns, the outer edge of
So
the
what they
road
do
is
in order to
raised
avoid
up,
that, look
which
at
is
that road, they banged it. I थोड़ा extreme कर लिया picture में. So the faster you go, the more banking you
the
need.
surface of the road at a
There,
turn
this is how the
makes an
road looks.
angle theta with the horizontal
Those angles are
surface.
small, like 7 to 8 degrees, 10 degrees maximum, something of that sort. Racing car, they need higher
This
angles.
results in the horizontal component of normal force n
sine theta.
But clear, right? Understood, no? When I say it is skidding, how it will skid. Clear with that? Now, what happens if you have friction on a banked road? Case 3, this itself is a question, so listen carefully. It's a good one. And this is also there for HSC 12 standard derivation. This is a rough banked road. Now, there are 2 cases here. Let's say if you're going very fast, that is maximum speed. So which way will you ride? So the car will try to go outside, right? Tries to slide outwards. Now, if you try to draw the FBD, I will keep the observer on the block. I want to use centrifugal force. So what are the forces? Normal reaction, mg. Since you're trying to slide outside, friction will be inside F maximum. The centrifugal force would be m u square by r. Please check any other forces. Since you're trying to go outside, the friction will act in the downward direction. Resolve the forces. If you resolve the forces, we get mg sine theta mg cos theta. This is F max. This is centrifugal force का component mv square by r cos theta. Because if this is theta, this is theta. So that will be mv square by r cos theta. And this will be mv square by r sine theta. So your normal reaction is not mg cos theta. Be careful. Don't always write blindly mg cos theta. It is mg cos theta plus abhi centrifugal force का component भी आ रहा है mv square by r sine theta. The normal has to balance both the mg component and centrifugal force का component. And in the along the inclined direction, if you see mg sine theta plus f max is balancing the centrifugal force का component mv square by r cos theta. What is f max? F max is mu into n. But what is n? N is not mg cos theta. So this is mg cos theta plus mv square by r sine theta is equal to mv square by r cos theta. So get v on one side and shift everything to the other side. M will cancel. So this will be g sine theta plus mu cos theta. This would be v square by r cos theta minus mu sine theta. So this is your maximum speed limit on this road, which is root over Rg sine theta plus mu cos theta by cos theta minus mu sine theta. Check. I can also multiply this and divide by cos theta. So this will become tan theta plus mu by 1 minus mu tan theta. Check it out. And here, if you see this term, if that cos theta minus mu sine theta becomes less than or equal to 0, that is, cot theta is less than equal to mu, then Vmax becomes infinity or undefined. That is, vehicle will never slip. That's a pretty good question. They can ask you, find the condition so that the vehicle will never slip on a banked road. Cot theta is less than equal to mu. So if you can adjust this friction value, no matter how fast you go, you will not slip on this kind of road. If denominator becomes negative, it becomes an imaginary number. So what it means is there is no known value of max which is defined. So that means it is saying you go with any speed it works. Have a look at this. This is your maximum speed limit. Similarly, now this is the minimum speed limit also. What if the car is going so slow? Then what will happen? Car will try to slide inwards. The friction will act upwards. Have a look at this picture. Any doubts? Any step you're not clear, please ask. Only thing that we did, we drew a centrifugal force and then we wrote the forces and equations and solving. Next one. Now for the minimum speed. So in this case, the car will try to slide downward. Now when you write the forces, mg, normal reaction, friction will be upward. This would be the centrifugal force, mv square by r. Same steps. If you write the normal reaction, this would be mg cos theta. This will remain same, mv square by r sine theta. But now this will be mv centrifugal force का component mv square by r sine theta cos theta and f max. These will balance mg sine theta. Again, substitute the same thing there. So we have mv square by r cos theta plus mu into mg cos theta. And we'll cancel. We end up with V minimum is Rg sine theta minus mu cos theta by mu sine theta plus cos theta का root. Again, you can multiply with the tan theta. You end up with Rg is tan theta minus mu. You get angle of repose. if you say V minimum is less than 0, so we get tan theta is less than mu. This is condition for no slipping at 0 speed. Think about it. Let's say you built a road and for some reason the car stopped on the banked road. Do you want the car to start sliding down? Or let's say there's a red signal and the car stops for a moment and the car starts sliding. Just think how weird it looks. So when you design roads on a banked road, you have to make sure even if the car stops on that road, it should not slip. So this is the condition for no slipping at 0 speed. Angle of repose basically. There. So if you have a banked road with a friction, then you get a speed limit, V max and V minimum. Generally, when these people build the roads, they make sure the minimum speed is 0. So if you have a rough banked road, you won't get a single speed, but you get a range of speeds where you're safe. This is what I said. If you're off a banked road, the friction becomes a safety factor. Check it out. So these are the 3 cases. The first case, it's a rough road. There's no banking. Smooth road, but there's a banking. Third is combination of both, a rough banked road. So here you're not depending on friction, you're depending on the normal reaction, which will not change with environment. And the answer, if you see, it is independent of mass. Whether you take a cycle or a lorry, it doesn't matter. So you need not worry like, am I designing the vehicle, road for vehicles, heavy vehicles or, maybe two-wheelers. It doesn't matter. The one place where you have a problem in banking, especially flyovers. This happened recently, 3-4 months back. They opened a flyover somewhere in Kurla or somewhere that side. People started going in, the bike started falling. On day 100 bikes have fallen on that road and they closed the bridge. Because you can't have a banking on a flyover, right? So whenever there's a turn, so something happened, it started slipping. So they had to redo the road. They actually, I think they put more of that, asphalt, that black thing, right? Tar road. Tar road actually gets a better grip and better friction. So something of that sort. Clear with this? This is about banking, everyone. This, what I showed you right now, maximum case 3 is itself is a problem. That can be asked as a problem. This is also the derivation in HSA. It's also the theory. It is everything. Put on any steps that you're not clear, please ask. Tan theta is 45, then it is why tan theta 45? What is so special about 45?
Theta 45.
So that's what, with theta 45, what is so special about it?
So then cot theta can also be equal to 1, right?
Okay, so
And I forgot to mention that even nu should be equal to 1.
तो सब बोल दो, तो सब assume करके तो सब, you just think in your head and you just tell one thing out. What will the other person think?
Okay, sorry.
You have to tell na theta 45 हो गया. हाँ sir, mu is equal to 1. I thought in my own head, so I forgot to tell you. मतलब how will the other person know what are you talking about? Then you can say, meaning if mu is equal to 1 and theta is equal to 45, yeah, you are satisfying both at the same time. That means the vehicle can't move, it should be at rest. So the 0 speed is there and maximum speed is also 0 only. You can do anything. Okay. Clear with this? Let's see a question based on this. Let's see a similar one.
So if mu is lesser than tan theta, then there will be negative inside the root.
Yeah, that means minimum speed is 0, right? There is no meaning of a negative speed, right?
Okay, sir.
The negative speed ka meaning is mathematically max is saying, boss, don't
Because
slip.
when we were doing for Vmax, we said if we get a negative inside the root, then
Yeah, that means it becomes undefined, right? Vmax is undefined. Means for any value of Vmax, I won't slip. That's what it means. So
Yeah.
here V minimum is negative means what? You can't have negative, right? Maximum you can have 0. Speed it is. Let's see another question. So this is a story I heard in Europe, right? They want to build a racetrack for the cars, and they brought some guy. They built the track, and then after building the track, they noticed something. No matter how fast the car goes, the time taken for one revolution is same. Now, if you make a track like that, so that means there'll be no first place, second place, third place, right? Everyone will reach always at the same time. So a variation of that. So someone designed a bowl. So there's a marble racetrack, okay? This is a smooth bowl, smooth marble racetrack. It's like that Beyblade ka track. So this track, right? So this is how you play the game. Let's say if I and Vojas are playing the game, we bring two marbles. We throw with our maximum speed. Whoever completes the revolution in one, in the shortest time, they win. So that means it is in our hands now, which is how fast we can throw. Getting it? So what something interesting happened. So when Vojas threw with a speed V1, it completed the circle. So I said, Chola, I will throw pretty fast. I threw it with V2. Now see, this is what happens. If you throw with a very high speed, you won't go in the same circle. You'll go in a bigger circle. Because when you throw very fast, the centrifugal force is so high, you go in a bigger circle. Something happens. So based on what speed you're throwing, you will go on a different path. So this is what is observed on this track. It is observed when a marble is thrown with any speed. The time taken for one revolution is t. Find the equation of the track. This does not happen for every shape. So what I'm asking is, so this bowl is there. I want you to find the equation of this curve. Again, when I say equation, I'm asking you to find relation y in terms of x. Like y is equal to some constant into x, y is equal to something like a into x power 4, anything. It could be some relation between y and x. The story is clear, right? Any ideas? Root mu plus 1. God, what is mu? It's a smooth track. Where did you create mu from? You have a very good imagination. You love to imagine stuff which are not there. You should be a writer. Where did you create mu from? And Ansh got 2 pi. Is that lon ray?
हाँ सर
So lon लेके आ गए. So lon 0 undefined है God. I mean there'll be a hole at the bottom of this track. Something will happen. Or
सर
lon
लॉन
x0 it will be infinity.
ओ अच्छा ठीक
तो
सर
मतलब
लॉन
तेरा ट्रैक
सर एक्स इज
ऐसा
नॉट
होगा.
सर एक्स लॉन के अंदर नहीं है
Then lon के अंदर क्या था? Lon t. Chalo, listen everyone. So when this is going in a bowl here, at any point here, let's take a small tangent here, theta. So can I say like this? This guy is going on this incline in this circle. Let the coordinates be x comma y. What are the forces on this? If you look at the forces on this, let's say it is going with some speed v. Let's say it is going with some speed v. Then this centrifugal force will be mv square by x. This would be your mg. This would be your normal reaction. So forces on the ball will be mv square by x. What I'll do now, I'll just convert that. V is equal to x omega. I'll write an x omega here. M omega square x. That is more convenient. This is mg. And I can divide n into components. You're going in a horizontal circle. Since this is theta, that is 90. This is 90 minus theta. This would be n sine theta. This would be n cos. Just like, this is similar to banking on a smooth road, isn't it? The banked smooth road, isn't it? This is similar to case 2 in banking. But the banking angle is changing. Smooth banked road. So if you write the forces here, we get n cos theta is mg. N sine theta is m omega square x. Tan theta is omega square x by g. But what is tan theta? Slope ty by dx. Send x on the other side. So we get dy is omega square by g x dx. So at every point the theta is changing. So tan theta is different, integrated on both sides. We get y is equal to omega square x square by 2g. This is a parabola. That is your equation, everyone. What is omega? Omega is 2 pi by time period, isn't it? Angle by time is the angular velocity. What is speed? Distance by time. What is angular speed? Angle by time. So you are completing 2 pi angle in time period t. Hope that is clear. Substitute omega, you get the answer. Have a look at this. So that is the main theme there. actually, if you can figure out it's a banking angle, इतना करने का भी जरूरत नहीं था. We know tan theta is v square by rg, ना? We already proved. And what is v? V is equal to x square omega square by xg, and tan theta dy by dx integrate. You'll get the same answer. So I took some random speed v at a random x coordinate and y coordinate, and there I got the equation. Check it out. Clear? Any doubts on this? Going ahead. This is a concept which we'll do again in gravitation, but we'll encounter this a bit. So we will see variation of gravity due to Earth's rotation. Now we know the Earth, when it is rotating, and let's say if you're standing somewhere here, now understand this is your radius r, but you're not going in this radius. You're going in this circle, isn't it? You're going in some other circle. This angle is called theta. Theta is called the colatitude angle. What do you mean by that? For example, if you take theta is equal to 0, it is an equator. Theta 90 is poles. So that is the meaning of colatitude angles. Now, if you look at the forces acting on this person, the centrifugal force is pushing him out, m omega square r. The normal reaction will be towards the center. And don't forget, mg is also toward the center. Huh? The weight is always acting toward the center. Now, if you resolve the forces of this man, we have normal reaction, we have mg, and this angle is theta. So we will have a centrifugal force component this way, which is m omega square, this is small r cos theta. Small r is this radius. And we can clearly see r cos theta is small r. So this person will feel the weight has reduced a bit. So he will think the weight is mg minus m omega square small r cos theta. And small r is nothing but capital R cos theta. So m omega square r cos square theta. This we can write as m into g apparent or g effective if you remember I taught you this in NLM. That means this person will think the gravity has become g minus omega square r cos square theta. So everyone on the earth will not feel the same gravity. It is not really much different because that r is very, that omega square r, this term is very small, it's negligible. So, but still there is a variation. That is your standard formula. At equator, theta is 0. So we have g apparent is g minus omega square r. So gravity is the least. That is the reason people prefer to launch rockets or satellites, near the equator. Gravity is less. And if you go to poles, the gravity is maximum. And how to find omega? Omega is nothing but 2 pi by time. And we know you cover 2 pi radians, that is full rotation in 86,400 seconds. 1 day. That is your omega. Yeah. So if they ask a question like this, let's say if you're trying to buy something, or let's say if you're trying to sell something, right? If I use a spring balance and a beam balance, which is a better instrument? If you are a trader and you're selling stuff, will you use a beam balance? You know what's a beam balance, right? And a spring balance. Spring balance is, it is based on the spring ka thing, and a beam balance, you know, there are two masses on the other side. Which one is a better one to use? Look at that. The problem with the spring balance, right? Spring balances measure what? They measure spring balances. They work on what? Work on kx is equal to mg. So if g changes, x will mess up. So they show maximum value at poles and least value at equator. So let's say if you actually try to, let's say if you try to buy gold at equator and sell at poles, will you make profit or loss? You're selling gold at equator and you're selling there at poles and everyone using spring balance. Will you make profit or loss? See, spring balance ka logic kya hoga? Let's say if it stretches 1 centimeter, it will think it is 1 kg. Agreed? That is how it is mapped. Based on the elongation, it will think the weight is there. Now, when you are at equator, to get 1 centimeter, the gravity is less, right? Mg is less. So you have to put more mass. Now see, k into 1, m into g. Since g is less, you have to put more mass. But when you go to the poles, g is more, so you have to put less mass. That means when you actually buy at the equator, you might be buying maybe 1 kg 50 grams, and when you actually sell at the poles, you might be selling 9, you know, that 0.9 kg or whatever. You actually make profit. Making sense? So people don't use spring balances. If you see these old gold shops, now they use electronic instruments, but people used to use beam balances. Why? What is the advantage of a beam balance? If it is messed up, it is messed up on both the sides, right? How do you use a beam balance? You put a weight here and put a weight here. If this is 1 kg, if it is messed up, even this will get messed up. Isn't it? Because both the sides mg and mg will always cancel. Beam balances are more accurate. Beam balances will show same value everywhere. Is that making sense? So if you buy, let's say 1 kg and go to the poles and it becomes 1.1 kg, what you measure also will become 1.1 kg. So it won't matter. You'll get the same amount of quantity. Now they can ask a theoretical question. If Earth suddenly stops rotating, will gravity increase everywhere? Does G increase everywhere? G increases at all points except poles. Poles पे तो constant है. Poles पे तो already there is no omega का effect ना. Already it is 0 that omega square r. G increases at all points except at poles. It remains same at poles. Third, next one say. Suppose if you are trying to send people into outer space, you know what is the biggest problem we humans have when we want to send them to outer space? Gravity. We humans, you know, have evolved to live in gravity. Once you go into a gravity-free space, we start having a lot of medical problems. Yeah, I think people are just switching off their cams without informing. Next time I'll just remove it from the classroom. So the biggest problem is, you know, we don't have a gravity, you know, a lot of medical issues will come. First thing, right now, even if you don't do any exercise, right, because of the gravity, your muscles are being pulled down, the weight So your body maintains a certain muscle mass even without doing anything. Ever seen this thing? Astronauts, when they come from space, they can't even walk properly. They're dragged out of the spaceship. It takes them a month or 2 months to recover. And astronauts normally, they work out every day 3 to 4 hours just to maintain a normal fitness. 3 to 4 hours workout just to maintain normal fitness. Because the muscles are not being strained. And biology says muscles are actually waste of energy. And human bodies, right, they always try to conserve energy. So if you put them in a situation where you don't need to use muscles will degenerate. And did you see this movie WALL-E? That small robot is there, it goes around. If you see that movie, right, all these people are in the space, what happened? They all become pretty fat. They don't have any muscle. They are moved around in some, that special carts and all. That's what actually happens. You have a lot of problems. Second thing, if you look at your human body, right, arteries and veins in the lower part, legs, are thinner compared to the upper part. The reason, when the arteries and veins are thinner, the blood can be pushed up with higher velocity. So you want the blood to go from legs to the heart, right, against gravity. But once you go into the outer space, what happens? There's no gravity. But the blood is still pumped upward with more velocity. So blood will start accumulating in the head. And your brain thinks you're producing too much RBC. You become anemic. You have a hell lot of problems. So if we humans have to go into the space and stay there, we need to create a way to somehow create artificial gravity. We still don't know how to create gravity, but somehow we have to create that kind of a condition. So one way to do that is to construct a big rotating cylinder. So if you make a spaceship, you have to make a spaceship which is a cylindrical thing and it is rotating. Then what happens? See, any person who is standing here will experience centrifugal force, which is not real, but he thinks it's a force. And if you can make this centrifugal force equal to mg, that means if you make omega is equal to root over r by g, all these people on the spaceship will think there is a gravity of g. And interestingly, how will this world will look like? In this world, if you stay in a world like this is how people will be there. They'll be standing like this. Means I can look at on the top and say hi to you. So these people will be like this. Because for him, centrifugal force is this way, right? So here, what is down? Down is away from the center of the spaceship. If you throw something, they go away from the center. So in this world, the buildings will be constructed this way. They will be pointing towards the center. So if you rotate with this omega, so people inside will feel the centrifugal force is similar to gravity. You can't tell the difference between forces. Centrifugal force plays the role of gravity. That is how you can survive in space. So far, we don't know how to manipulate gravity, but we can create gravity type conditions. So if you have to send passengers to, this Elon Musk is trying to send people to Mars. So this is the first thing you need to do. On the spaceship, you need to create a cylindrical region, at least in the part of the spaceship. So where these people can go and stay there every day, at least for a few hours. So in that cylinder, they'll feel the gravity kind of conditions and they can go back and work whenever they need. So their living quarters has to be a rotating thing. This is how it would have looked if you have seen the movie Interstellar. So this is the scene, if you remember, this guy comes back and this is the climax thing.
Let's take it slow, sir. Nice and easy, Mr. Cooper. You are extremely lucky.
So this guy, if you have seen the movie, this guy comes back to that thing from the black hole.
With only minutes left in your oxygen supply.
Look at this scene. People are playing baseball. He hits the ball. Did you see how the world is? Did you see how that world is? It's a big cylinder. The climax of the movie, right? They're in a spaceship near Jupiter. That spaceship, can you see that there's a whole cylinder? You can look at the scene carefully. The boy hits the ball. The ball goes like this. and see how he looks. It hits the house on the top. They construct the whole city inside a cylinder and the cylinder is rotating. They created an artificial gravity situation there. And that's how they can survive just like a regular world without any issues. And then he asks, where are we? Where am I?
Cooper Station.
There. That is your interstellar. Okay. So that is one. So with that, we are done with the uniform circular motion part. So next class, when we catch up, we'll be doing something called non-uniform circular motion. Now the speed also will change. So we'll be working on that. So okay. So that will wrap up for that day. So do make sure to go through this. We did almost 26 problems. You can start doing uniform circular motion parts. You can handle it. After the next class, even non-uniform circular motion, most of it will be done in the next class. Okay. So, and do resolve the last week of paper. We'll be discussing it on Thursday as usual. So any other doubts, anything you can stay back and ask, or you're free to leave. So take care, stay safe. I'll see you on Thursday, same time.